Hello, everyone. Welcome to the December 13th OpenShift Commons General Call. Today we have a special guest. I am going to actually let you introduce yourself, and we appreciate you and work with you a lot, both downstream and upstream. And please also describe what you do with CNCF storage. I think that's really interesting.
Okay. Yeah. Hi, everyone. My name is Raffaele Spazzoli. I am a consultant at Red Hat. I've been working on OpenShift now for almost since the beginning, so more than 7 years. And I'm now in a global office. It's a services office of technology. So we follow high profile customers all around the globe. I also participate as a chair in the CNCF Storage Tag. The Storage Tag is the technical advisory group for storage cloud native products. So we help these products be known, and also if they want to become part of the CNCF, we help them graduate. That's what we do. But obviously, the idea there is to promote the concept of storage. There is a lot of focus. There was initially in cloud native, there was a lot of focus on stateless, but in storage, we look at everything that is stateful, essentially. So that includes messaging, databases, also not just volumes, disks and that kind of storage. And we have so far published 4 white papers. We have one general white paper on storage, one around performance, how to measure performance on storage for storage products, and then one around disaster recovery. And the newest is around storage, particularly in Kubernetes, not just in general cloud native. So that's more or less where we are with that group. Today, the idea was to talk about disaster recovery with 4 applications that run in OpenShift. Okay. So I'm going to talk about some of the approaches, and then maybe focus at the end, if we have time, a little bit more on what we call, in the storage tag, what we call cloud native disaster recovery, which is the active one, as we will see in a minute. Before I go forward, though, I just want to point out this. Typically, when I talk about disaster recovery, is really about the applications and the guaranteeing the business continuity of the applications, and not so much about the recovery of the OpenShift clusters. So as you can imagine, we have multiple data centers or multiple cloud regions, and in those failure domains, we run multiple clusters, and in the clusters we run multiple applications. The only thing that we care about really is that the applications keep providing their services. I don't focus much on recovering a cluster. In fact, I would advise I encourage my customers to become good at rebuilding clusters and repopulating it with the right configuration, which includes infrastructure configuration and what the tenants were deploying, so what the developers had deployed. But I don't try to save the state of the cluster and restore the state of the cluster if a cluster is lost. So with that in mind, there is actually no OpenShift in these slides because we just focus on applications. And these are the 4 patterns to do for disaster recovery strategies. Now, these patterns, obviously, they represent a single application, right? And you can see in a couple of failure domains, or 3 on the right, for the rightmost one. But obviously, the reality is much more complex. In in a real IT data center, there are multiple applications that could be using different patterns, and also they depend one on another, right? So there are chains of dependencies. Maybe one has to recover before the other one can go. So reality is way, way more complex than these 4 patterns, but to make this subject treatable at some level, we have to start from here, or at least I suggest to start from here. I heard the beep. Was there a question? No. Okay. Okay, so from left to right, we have patterns that get better and better. Okay, and the way you measure the performance of a disaster recovery pattern is via RPO and RTO. These 2 metrics essentially measure the RPO measures how much data loss you have because of a disaster, and RTO measure how long the outage is because of a disaster. So as we move to the right here, they get better and better up to basically 0 for the rightmost one. And so we have backup and restore and volume replication. I think they're self-explanatory, right? Backup and restore, we do backup and then we restore the state. And for volume replication, we replicate data at the volume level. These 2 are active passive type of patterns, as you can see from the top line here. Okay, and also they leverage storage capabilities. As you can see, all the work happens at the storage level. So you need the proper storage capabilities here. The other thing that we notice is that there is a global traffic manager or a global balancer. Okay, because it's active passive, somebody has to switch traffic from one side to another. The other thing that sometimes customers ask is, do I have to keep this the failure side running or not? It depends, right, on the approach. When there is the dotted line, it means that it doesn't have to be running, which may save you some funding. But so I have to turn on storage or the volumes and the application only when I do the restore. In this case, instead, I have to turn it on. I have to have at least the volume on. I can turn on the application just when I want to do the disaster. Start the disaster recovery strategy. Then we have the next 2 is where we are moving the responsibility of replicating the state to the middleware. So this could be a database or could be a messaging system or a cache. But in one case, we have the passive primary, secondary pattern, or maybe master slave pattern. Different middleware call it in different ways, but it's the concept that one is the instance that received the writes, and it's responsible for synchronizing another instance that has the same state and perhaps can respond to some of the reads. And again, this is an active passive scenario where, like I said, all the traffic, or at least all the reads, have to go to one specific place until you switch the traffic and because there is a disaster. And finally, we have an active scenario where every instance here can receive writes. And to implement these kind of patterns with a strongly consistent transaction semantic, meaning once I do a write, once I make a write, the write is propagated everywhere, and I am sure that it's not going to be lost, even if I lose the region in which the write was actually occurring, which I was actually talking to. And then I need 3 regions or 3 data centers. So as you can see before, I could do it with 2, but if I want strong consistency here, I need 3. And this is a consequence of the CAP theorem. CAP theorem is one of the few theorems that exist in IT. It's good to know. It's something that we should know. If I don't care about strong consistency and I'm okay with eventual consistency, then I could just have 2 regions. But typically, if you're doing a database, if you're using a database with SQL semantic, then you expect ACID semantic to use transactions, and then therefore you want strong consistency. Okay, so usually when I talk to the customers about these patterns, what I try to advocate is that when we build the platform team or the developer team, right? We usually talk to platform engineers. So when we build the platform team, my suggestion is let's make these capabilities available to the developers, right? To the users of the platform, and let's not make the choice for them. We just give them the capability to implement whichever strategy for disaster recovery. This is a very, very hard proposals for the average company to accept, because normally what really happens is that the disaster recovery is a responsibility of the infrastructure, and it's very seldom given to the dev teams to be responsible for their disaster recovery. So if you want your disaster recovery to be a responsibility of the infrastructure teams, the 2 here on the left, where everything happens at the storage level, which is owned by the infrastructure team normally, are more suitable. Because instead here on the 2 on the right, basically the configuration needs to happen at the middleware level, which is more likely to be owned by the application teams. But if we can agree that as the platform team, we just want to provide these capabilities, so then dev teams can build their own disaster recovery strategy, then the next logical question is, what are those capabilities, right? So I have a slide here for the capabilities. So for each pattern, we have storage capabilities, network capabilities, and workload capabilities, right? So as you can see, for backup and restore, I needed some level to be able to configure that I want a backup, and then at some point I will want to do a restore, and then I just need a global load balancer. And then for the synchronous or asynchronous volume replication, I need this ability to say that I want volumes to be replicated, right? And then I still need the global load balancer. As you can see, the global load balancer is always there. But then when we move to middleware, where I'm going to hide this, where we have either master slave or fully distributed workloads, then we need, first of all, we need a middleware that is able to do this kind of, to be configured in this kind of ways. But also we need this sort of east-to-west communication capability, right? So I call it east-to-west path. So between the data centers or between regions, there must be a way for these middleware instances to be able to communicate. And if we are deploying these applications in a Kubernetes cluster or an OpenShift cluster, and therefore these are pods, there has to be some way for each pod to communicate exactly with other pods. They cannot go through a load balancer because these are stateful workloads, and they need to communicate with each individual instance for this type of transaction replication to work or state synchronization to work. So we need a way to build this network tunnel, as I called it here in the picture, okay, between between the pods of Kubernetes instances, and you know that pods are running in a software-defined network that is some way isolated within the cluster. So we need to build this network tunnel between the software-defined networks. Okay. Next slide. So if we agree, like again, if we agree that these are the capabilities that we need, then how do we build them? Well, we have options, right? There are several products, add-ons, I would say, to a Kubernetes or an OpenShift cluster that you can implement to enable those capabilities. So for backup and restore, I have several products here, as you can see, and there are many more. To be honest, I just put some of them here with no particular, I'm not saying that these are the best. I just wanted to make the point that there are options, and there are open source options and also more commercial options. In the Red Hat world, we have this operator called OADP, which you can install and will let you configure disaster recovery. There are more advanced products where you can do more, you can do schedule of backup and restores and more advanced configuration for backup and restore. For volume replication, I have on the OpenShift side, Data Foundation, and then we have also Portworx, and probably there are other kind of storage where you can configure replication between volumes in 2 different clusters. Okay. For global load balancing, there aren't a lot of operators that do global load balancing. So just to be clear here, the capability is not to have a global load balancer, because global load balancers already exist, right, in your organization. The point here is that we would like to configure the global load balancer based on the status of the applications that are running in these clusters that need to be globally load balanced. Okay, so we would like to be able to do that automatically, and there aren't many operators in this space. And the reason is that in order to configure a global load balancer, you need to be able to observe the state of multiple clusters at the same time and decide where the application is deployed and how to load balance there, right? But today, operators are mostly cluster bound, so they can only see the horizon for what they can see and watch is always within the cluster. So you can use an external automation to configure the global load balancer. So I have here, for example, Ansible that is configuring a global load balancer. So you would have, when you deploy an application, you would have a way to trigger this automation. So when you deploy to multiple clusters, your application to multiple clusters, you maybe have a way to trigger this automation that goes and configure the global load balancer. Or there is an operator, this K8GB, this is an actual operator that can configure a DNS-based global load balancer. So if your global load balancer is DNS, you can use this operator. It's not supported by Red Hat, but it's in the CNCF, and I've used it. It does its job. Okay. For the east-west path capability, remember, I cannot see you guys, so I'm not sure if you're following. Just give me some feedback. Feel free to interrupt or give me some feedback anytime. East-west path, so this ability of pods, the pods can want to be able to communicate with each other across clusters. This is something that some CNI products like Calico and Cilium give you out of the box. For OpenShift, our CNI network doesn't do it out of the box, but you can install this Submariner project, which we fully support, and it will create this network tunnel over an IPsec or WireGuard channel. If you're looking at middleware products that can be installed in primary and secondary or master slave configuration, there are things that you can run on-prem or even in the cluster, like the classic Postgres, MySQL, but also Oracle, SQL Server, DB2. The classic incumbent SQL databases cannot be run that way. They were designed, they are essentially monolithic, vertically scalable products that can do active passive. It's very hard for them to work in active manner. And also the cloud providers which give you these same products but wrapped with their services or as a service also work more or less the same way. Even if they tell you that you can go across region like Aurora, the reality is that one of the region is active, the other regions are passive. Okay. Then there is a completely new generation of products that is built to be, fully distributed. That is fully distributed. So these are fully distributed stateful workloads or middleware, which can really be installed in an active fashion, and they allow you to implement this one, right? This active setup. And so for databases, we have things like Yugabyte and CockerDB. Kafka is an example of a middleware. MongoDB is an example of a NoSQL database that can be installed that way. Vault can be installed also that way. Vault uses Raft internally for state synchronization and so on. Notably, Cloud Spanner here, Google Cloud Spanner. This is the first. This was the first SQL database that was fully distributed. Okay, Google came up with this product a while ago. It's still unparalleled. I mean, I don't think the other Amazon and Azure have something like that. When you spin up a Spanner instance in Google, you have a SQL database that is globally and distributed, so you can access it from any time, any place in the world, and it's fully consistent. When Google wrote this product, they also published a white paper, and people started looking at that white paper and figured out that they could recreate the same technology outside of the Google data center. And that's how Yugabyte and CockerDB were born. So they're kind of an offspring of Spanner. Now, these products are 6-7 year old, I think. So they are startups for sure, but they're getting to the point where they're not startup anymore, and they're starting to have a significant market. Okay, so I'm gonna skip this a little bit. I'm gonna go over this very quickly. If you do this setup in the cloud, I think one thing to pay attention to is the network traffic, because in the cloud you pay for network traffic across region, which would be your failure domain, right? So either way, if you do volume replication, transaction replication, or state synchronization, there is always network traffic. And if you have a lot of transactions in your stateful workload, then you have a lot of traffic. So the main consideration here is to keep an eye on that cost factor, because you don't really have it if you build this infrastructure, these solutions on-prem. So I just want to go over two of these setups of this configuration a little bit more in depth. We're going to go over the volume replication because it's the one that Red Hat supports. And then we're going to go over the active because it's the one that, everything else being equal, everybody should be trying to do this one, right? Because in this one, maybe I haven't gone into the details too much of what happens when you have a disaster. But when you have a disaster in this one, and you lose one of these, right? the global load balancer automatically steers the traffic to the regions or data centers that are healthy, and you don't have to do anything. Like the stateful workload automatically reacts and rebalances the replicas, and so that it can continue to serve traffic. So this is the only one where the reaction to the disaster is completely unattended and happens in seconds. All the other ones, the reaction to the disaster must be, I mean, at least the traffic, somebody has to go and change the traffic manually. So active is where your system reacts very similar to, when there is a disaster, reacts very similar to how it would react for an HA, high availability event, where something breaks, right? And within like a replica of something breaks and all the traffic goes to the other surviving replicas. This is the same. It's the same here, except it's happening at the data center level. So everything else being equal, this is probably what everyone should be looking to do. So I want to go a little bit more in depth on that one. So for volume replication, we have a product called ACM, right? That can help you with OADP, with our data foundation product, can help you set up both synchronous replication and asynchronous replication of volumes. We call synchronous replication metro DR and asynchronous replication regional DR, but it's really those concepts that we were talking about above. So if you want a supported way to do it, to do disaster recovery and manage it at the infrastructure level, like I was saying before, right? You can choose infrastructure level or doing that at the application level or developer team level. But if you want the infrastructure to be responsible for everyone and take care of disaster recovery, this is an approach, right? It's an active passive approach, but it's fully supported. And then for cloud native disaster recovery, I have this table to try to compare and contrast this cloud native disaster recovery with the more traditional disaster recovery. Cloud native disaster recovery is what we call active. So this pattern here that I've just described, we call it cloud native disaster recovery in the tag storage and in the disaster recovery white paper. Because the idea is that while this pattern has always existed, with cloud native approaches where it's easier to build complex configuration because we use things like GitOps and API, right? Self-service API. So with the cloud native approach, is actually now reasonable to think about bringing up these architectures. It is also not true the narrative that building these architectures where RPO and RTO tend to go to zero. The narrative was if RPO and RTO go to zero, the cost increases exponentially. This is actually not true anymore because you can build these architectures with essentially open source projects. So if you're willing to put in the effort and create your configuration and with tools like GitOps and control it with cloud native approaches, you can actually build this architecture today. So what is the difference? Well, first of all, it's like we said, it's active. All more traditionals are active passive. So active allows you to distribute the workload more evenly, right? Maybe even process the request more closer to where it was originated. What is detecting the fact that we are in a disaster situation? It must be a human when you have active passive, but it's going to be autonomous. So the system understands that there is a disaster by itself. Now the human trigger is generally a problem because if you have ever been in those situations, it takes some time to get the person who has the power to say, this is a disaster, like let's triggered the disaster recovery procedure, it takes some time to get him on the phone. So there is always an additional lag to the outage or to the duration of the outage, just because we have humans in the way, right? And then the procedure itself, when in traditional DR, in traditional companies, right, it's a mix of manual and automated tasks. It's a thing that we do so rarely that it's hard that it's fully automated. And yes, there are the biannual exercises that week that is painful for everyone, right? But the reality is that it's never perfect. In cloud native DR, it's mandatory, fully automated. Everything is going to be automated and controlled essentially by the middleware, so by this layer here, and the global load balancer. RTO, RPO, like we said, are close to zero. In fact, they are it's exactly zero in terms of data loss, but and it's close to zero for the outage, because it's just the time for the health checks from the global load balancer to realize that one of the regions has a disaster, and the global load balancer has to swing the traffic to the healthy ones. And then we talked about the ownership, right? Usually for traditional DR, it's the storage team that owns the process. But if we want to implement this kind of cloud native disaster recovery, it's going to be the application team or whoever owns the middleware, but typically the application team. And then also we have talked about this, right? The capabilities for traditional DR are mostly located in storage space, so backup and restore or volume replication. But for cloud native disaster recovery, we need east-west communication or east-west path, and a good global load balancer with this ability of doing health checks and perhaps advanced load balancing strategies. So I talked about the fact that after Spanner, there was a new set, an offspring of new products, right? But the real trigger was to this new set of products was really the CAP theorem and the understanding of this theorem. It's pretty recent. For example, it wasn't when I went to study at the university, they were not explaining it. But this theorem essentially explains the fundamental rules about distributed system, stateful distributed system, and the fact that if you want this system to be able to keep working in a situation where the network is unreliable, so there can be network partitions, then you can only choose the system to be either consistent or available, but it cannot be both. So either every instance sees a consistent state, or every instance is available, but cannot be both. So a good way to understand what your distributed system can do is to ask that question: right? Is it did they make the choice to be consistent, or did they make the choice to be available? And then if you look at this new generation of software, they can be exposing at the API layer. This could be a database, or it could be a messaging system, or it could be a cache. But the reality is that the anatomy, the internal anatomy of the products are very, very similar. And usually, so there are replicas, which gives you the reliability, right? So there are instances of the product that contain the same data, right? And then when one of these replicas receive a write, for example, it needs to coordinate with the other to make sure that enough of them, the majority of them, has the new information and has stored the new information to the volumes, to the storage. And there are partitions. Partitions allow this middleware to scale horizontally, almost in an unlimited, in an unbounded way, right? And if you request, if it makes sense for the API that is being exposed to request a transaction that goes across partitions, then you need an inter-partition coordination protocol. And so these are these two other things. If you want to understand exactly what your distributed stateful workload, how it works, you should also ask about the inter-replicas synchronization protocol and the inter-partition synchronization protocol. But by and large, the point is all of these software work in a similar way internally. Okay. And then I would like to close with an example here of for deploying Cockroach DB. This is one of the products that I experimented with, and in particular, in this case, I think I'm depicting a deployment across in AWS. I think this was AWS. So across 3 AWS regions, there were. So I had 3 OpenShift cluster across these 3 regions. Each cluster had 3 instances of Cockroach DB, and so in a total of 9 instances. They were all communicated with Submariner as the network tunnel. So it was a single logical cluster of, so a single logical database made of 9 instances of this Cockroach DB database, and distributed across North America. And we ran on this topology. We ran some performance tests. We saw that it was scoring, I think, 96% of the TPCC standard test. You can go and this TPCC is the way to test databases. So very close to a monolithic instance, which they normally score 98%, something like that. So it was very performant, and at the same time, we experimented by taking down virtually taking down AWS regions, and we saw that the traffic was still being served. So the database kept serving and didn't have any data loss. You can read more about these experiments here in this article if you're interested. I have another one. We ran a similar experiment with Kafka in Google. It was pretty much the same setup. Like I said, these products tend to work with similar concepts. But yeah, again, we ran performance test and disaster recovery test, and again, everything worked fine. Obviously, with Kafka is very much used for latency sensitive use cases, right? Scenarios. So with Kafka, if you wanted to distribute Kafka across North America, you will pay a little bit the latency price, right? So this cluster of Kafka cannot ingest at the same speed as it would if it were like in a single location with all the instances with very little latency between each other. Nevertheless, if you can accept the latency that this setup gives you, this is a very much stable deployment of Kafka, meaning you will never lose a message with this one. Okay, so that's it. That's all I have. I think we can open for questions.
Any questions? David, did you get any in the doc?
I didn't get anything on the chat, and I don't think we got any doc. Dwayne's doing, or Mr. Branch is doing the notes on the doc right now.
Nice. Thank you.
I have a question. You said there's a lot of exercises that you need to practice probably throughout the week or making sure your system is ready. I would imagine one of those things is putting in a patch with zero downtime. Like, what region would go to? How do you practice that?
I couldn't really understand it very well.
Yeah.
The microphone, it's a matter of, yeah, it was very disturbed.
Hello, can you hear me now?
better.
Okay, my question was, I know that you're doing a lot to test out, your system with exercises for performance for recovery. What kind of exercises do you use to deal with a patch to have zero downtime?
What kind of exercise do I do to deal with what?
Like if you have to patch the system, some security patch, so it doesn't, go into crisis or anything.
So the question is, how do I test a disaster recovery scenario?
Yes.
Yeah, so the best way to test it, in my opinion, is to create a situation where this connectivity is completely is severed. So one of the region where we pretend there was a disaster, is unreachable. This is better than shutting down these machines, because if you shut down a machine and I try to connect to that machine, I get an error that says, you can't talk to this machine. It's way easier for a system to react to an error than in the other scenario where you disconnect, where you essentially create a disconnect here, where the connection is severed. Because in that scenario, you send a packet, you try to connect, and the packet, you don't get any answer. The packet is lost. So when the packet is lost, you don't know if on the other side the packet was received and processed, right? So it's harder for a system to manage a situation where the connection is severed versus a situation where when I try to connect, I get an error. So when I test this disaster recovery scenario, I just in all the cloud providers, you can just isolate regions and essentially create a firewall rule where all the packets are going to the void, going to a black hole, and then so this become isolated. You cannot connect to this anymore. But then you observe what happens on the other two, which you're still able to connect to, and you see how the system would react. Did I answer the question?
I don't think so. I think he was asking, and correct me if I'm wrong, Dwayne, if you were patching Cockroach, the database on one of them, how do you avoid the downtime of Cockroach as your diagram says? Let's say I have to patch a Cockroach database in US1 on the lower left, the lower right or left, excuse me. How do I keep the DR working if I'm patching that instance of Cockroach on that in that instance on AWS, etc. Was that the question you were asking, Dwayne?
Yes.
Does that help understand the question?
Yeah, I think so. Let me try to give you an answer, but I'm not sure I fully understand the depth of the question. So when I patch, obviously you could do a rollout of the new version of Cockroach. So maybe this guy goes down. I built this with 3 replica exactly so that when one goes down, I can still serve the traffic with the other 2. And so I can propagate the changes to this, to this, to this, and then I start changing here. So there isn't an outage. There isn't even a local outage when you roll out the patches. If you roll out one instance at a time.
But yeah, go ahead, Dwayne. Sorry.
Yeah. Well, that's good. Well, thank you.
I have a follow-up for that question. You were thinking, on the US1, let's say you have the US1 there and you want to patch one of the Cockroach databases on the US1.
Mhm.
Don't you have to have 3 instances of Cockroach DB up and running on US1 for a quorum So how does that work exactly? Because if you take down one, that means you broke the three quorum or the three instances of cockroach on US1.
No,
Example.
no, this is a logical cluster of 9 instances. It's not 3 cluster of 3 instances. It's a logical cluster of 9 instances. So if I take an instance out, I have 8 instances going. It's still a quorum. A very good quorum. No problem. Does it make sense?
Yes. Yeah, it does make sense. I'm just curious because, when I look at your diagram here, it's like there's like 3 of 3 on here. And so, not understanding, not catching the whole point of having all of these function as a quote unquote one single database.
Yeah, I could have built it with just one instance and it would still work. But I also wanted local high availability, not just global high availability or global disaster recovery resilience. So that's why I have 3 instances in each region. But it's a single logical database made of 9 instances. So as long as you don't lose 5 of them, you can still go on. It can still work.
We had another question in the chat. Dan brought up, are there latency requirements for that local cluster between sites?
Mm-hmm. No, these products, they can work with they have, the latency they can tolerate is configurable. But like I said, if you have a lot of latency between these regions, your transactions are going to be slower. So a write is going to be slower. So the real question is, given the application that you want to run on this database, or given your use case, can you tolerate that latency? And typically with Raft, all of these products tend to be based on Raft. There are 2 replica consensus protocol, Raft and Paxos. Paxos is the old one, Raft is the new one. So all the new ones use Raft. With Raft, the latency is essentially the round trip, so back and forth between the 2 closest regions. So if let's say that this is east, this is west, and this is middle of America, right? So between east and west, this is obviously longer latency than between east and the middle. So that you can expect if this was our system, you can expect a latency that is 2 times the latency between the shortest path. So it would be between east and center. And so you have a reasonable idea. You can predict what the latency is going to be for an individual transaction. And if your use case can accept that, then you are in a good place. If your use case cannot accept that, then you cannot use this distributed approach, and you probably have to create a local instance and maybe a passive instance with a active passive disaster recovery approach. So maybe I wasn't too clear at the beginning. I'm not saying that this is always the best solution, but when you can apply it, it looks like it should be the best solution. Right? When it's possible for the use case, use it.
Do we have any other questions? Dan, if you want to go ahead and go into the notes and make sure we captured all the information that you were asking for your question, just so that we have a good, clear picture. I do have a kind of a question-ish for you. Back on one of the slides, you said that on the active passive for disaster recovery, you had mentioned that the storage team has mostly the ownership of the active passive. and the applications are for active. Where did you get that information from the storage team being the system owner for the DR for active passive, excuse me. Does that make sense?
Yeah, it's more about an observation of the reality. What happens is, for at least my experience talking with customers, the business continuity plan for an application is always a responsibility of the dev team or the business unit. But what they usually do is they look at the storage team and say, what can you give me in terms of disaster recovery for the storage? And whatever the answer is, that's going to be their strategy. So while perhaps formally the responsibility is still on the application teams, in reality, it's the storage team that drive the disaster recovery for the entire data center, right? In most traditional situations. But when you move the responsibility of replicating the state at the middleware level, here at the database level, you don't expect anything from the storage team. This is just simple dumb volumes, right? They don't have any relationship there is no relationship between this volume and this volume and this volume. It's just give me storage. As long as it exists in that data center or in that region, I'm fine. So now the responsibility to make sure that disaster recovery works is at the middleware layer. So let's say middleware layer, whoever owns the middleware layer is the real responsible. And typically I see that be a responsibility of the developers more than an infrastructure team. So that was the reasoning there.
I'm just going to throw this out there question. I understand the active being the applications, but more from active passive standpoint, I wouldn't necessarily go from the storage standpoint. It's everybody from the IT team, from connectivity, the storage, everything. Because obviously, when you have a disaster, everything's impacted. Not necessarily just the storage standpoint. And that's what I was trying to understand.
Yes.
Because
that's fine. Sure.
Because when you have a disaster, it's everybody. It's an all hands type thing. It's not necessarily just falls on one team. That's why I was asking the question.
That's true. I think perhaps so maybe if I say better, the team that is more responsible than other of making sure that the state is replicated and without a replicated state, there is no point in doing a recovery, right? It's the storage team. Yeah, maybe if you say it that way, but everybody participates to the recovery procedure. Absolutely, I agree with that.
You good, Dan? I saw the question in the chat. Are you good? Okay. Do we have anybody else questions on the chat or in the and Dwayne, do we have anything in the notes for questions?
I think we're good.
Other than that, I think Katrina, if you want to Karina, if you want to close us out, I think we're good.
I was enjoying having you be host for a while. That was nice. Turn my camera back on. But thank you, everybody, all our volunteers and all our community members. And thank you, Raffaele. Very much appreciate it. It's always a good discussion and a very, very important topic. So, and with that, we will have one last community call next Wednesday, as well as EdgeSig is meeting again on Tuesday, at least for the new year or until the new year. You can tell I'm ready for PTO as well. So, but we'll see you next week. And thank you again for joining us. See you all soon.
Bye-bye.
Stopping the recording.